Hello YouTube! In this video I'm going to introduce a new player in the scientific realism debate. This is known as tautological scientific realism, and it was first defended by Carl Hoefer in the article Scientific Realism Without the Quantum. Now, in order to understand tautological scientific realism, it's worth saying a little bit about the earlier versions of scientific realism. I do have a whole series on scientific realism, which I'll put up in the comments, so that's worth watching, at least the introduction to that if you're not familiar with the realism debate. But anyway, scientific realism. This is the view that we are justified in believing that our best scientific theories are at least approximately true. Scientific theories attempt to provide descriptions of the way the world is, and we can be confident that at least the basic commitments of our best theories are close to the truth. Obviously, there are lots of things that we still don't know. Doubtless there are many respects in which we are mistaken, but even so, realists are optimistic that we've gotten things broadly correct. So there really are protons, electrons, mitochondria, black holes. These things really do work in the way that our best theories describe. That is realism. And, well, that I suppose is probably a fairly common sense sort of attitude to the sciences. But why should we be realists? Well, traditionally, realists have appealed to inference to the best explanation. Science is incredibly successful. It allows us to predict and control nature to an unprecedented degree. Scientific theories make remarkable novel predictions. For example, general relativity's prediction of the degree of light bending caused by large masses such as the sun. We apply scientific theories in the development of new technologies. So what allows me to make this video and put it out into the world is the control of nature that is supported by science. How is this possible, right? It would be a miracle if science were able to support such successes if its theories were not even approximately correct, like if its theories were completely mistaken. So the best explanation for the success of science is that scientists have uncovered the facts about the way the world works. So inference to the best explanation tells us to believe the hypothesis that best explains the data. The hypotheses that best explain the data, both the data accumulated by scientists and the data about science, such as the remarkable success of science, well, the hypotheses that best explain this data just are the well-confirmed theories of our mature sciences. The truth of the Big Bang hypothesis is the best explanation for data such as the cosmic microwave background radiation. It's also the best explanation for part of the best explanation for the remarkable success of astrophysics, etc. So, inference to the best explanation has long been one of the central arguments for scientific realism. And I mean, the point being made here is, I think, pretty intuitive, right? I mean, look, before you start thinking about this philosophically, you probably just assume that there are indeed electrons, whereas you probably don't believe that there are the Homeric gods. Why is that? What's the difference between, electrons and the Homeric gods? Well, the difference is that the theories that postulate electrons have been so successful. They make such remarkably accurate predictions. Theories about Homeric gods, they're not so successful, right? They don't make good predictions, and they've never given us things like cathode ray televisions. So, inference to the best explanation plays an important role traditionally in the defense of scientific realism. Now, there is a big problem with all of this. The problem is that inference to the best explanation is extremely controversial. So one issue here is, well, why suppose that explanatoriness is a guide to the truth? We assess explanations according to, various theoretical virtues like simplicity. So, famously Occam's razor, do not multiply entities beyond necessity. But why suppose that nature is simple? A lot of people have argued that simplicity is merely a pragmatic virtue, and it doesn't really tell us anything about the way the world actually is. Moreover, even if explanatoriness is a guide to the truth, why suppose that the true explanation is among the explanations that we have actually considered? Inference to the best explanation involves taking a set of potential explanations, and then you assess each of them. You have explanation 1, explanation 2, explanation. You have a set of explanations, you assess them, and then you accept the one that best meets or best ways, it provides the sort of best weighting, best balance of certain theoretical virtues. Well, that kind of procedure is only going to lead us to the truth if the true explanation is among the explanations that we have actually considered. But there's, I mean, what's the guarantee of that? Maybe we're selecting from the best of a bad lot. On top of all of this, we know that the scientific method does not inexorably lead to the truth, because there have been plenty of cases in the past of theories that were successful but were ultimately displaced. Newtonian mechanics was remarkably successful. To this day, we still use Newtonian mechanics to send probes to Pluto, but it was displaced by general relativity. These sorts of challenges have proven to be pretty tricky for realists. Now, I've outlined all of these at length in previous videos, right? So, if you want more detail on any of this, again, look in the comments. I'll put a link up to other videos where I've talked about all of this stuff. But this is just a very brief outline of the shape of the debate so far, right? Just like why we might take inference the best explanation seriously and what some of the problems are with doing that. Now, we enter tautological scientific realism. So, what is tautological scientific realism? Well, first of all, tautological scientific realism claims that realism is justified for the central law of contemporary science. What do we mean by central law? Well, there's no precise definition of this, but think about, the sort of basic theories that will be described in, high school science textbooks, right? So the modern evolutionary synthesis, the periodic table, basic cell biology, theories concerning DNA replication, cell division and reproduction, chemistry, like basic chemistry of how atoms bind into molecules, and then certain claims about molecular composition, so water is composed of H2O, our understanding of the basic properties of atoms, right? Atoms are composed of protons, neutrons, and electrons, and then there's related processes like radioactivity, claims about stellar evolution and nucleosynthesis, the synthesis of elements in the cores of stars, and so on, right? These basic, this is the contemporary law, right? These sorts of theories that have been very well established for several decades now, and that, again, the sort of things that you'd find in like undergrad textbooks or high school textbooks. So this is what realism is justified for. So that's pretty standard. A lot of realists would agree with that. The key claim of tautological scientific realism is that the reason why realism is justified is because it is inconceivable that these claims are mistaken. So crucially, according to Hoefer, this means that tautological scientific realism does not depend on inference to the best explanation. Rather, tautological scientific realism's claim is that we can't even conceive of any way in which these theories could turn out to be wrong, unless we end up endorsing radical skepticism. So basically, assuming that radical skepticism is off the table, we are forced to be realists. The only way to conceive of the central law turning out to be mistaken is to invoke a radical skeptical hypothesis. What do I mean by radical skepticism? Well, this is the sort of skepticism that has come up for thousands of years in philosophy, right? Think about things like the brain in the vat scenario, which proposes that you don't have a body, all your perceptions are misleading, really you are a disembodied brain in a vat being controlled by a supercomputer. Or Descartes' evil demon scenario, which proposes that you're being deceived by a super powerful evil demon. Or the dreaming hypothesis, which proposes that all of your experiences are a mere dream. The radical skeptic says you have no basis on which to rule out any of these hypotheses, and since you have no basis on which to rule them out, you have no justification for believing any common sense claim about the external world. So the argument would go like this. If you don't know that you're not a brain in a vat, you don't know you have hands. Premise 2, you don't know you're not a brain in a vat. So, conclusion, you don't know you have hands. And of course, you can substitute any claim about the external world for you have hands. Radical skepticism throws doubt on everything. And radical skepticism doesn't have anything in particular to do with science, right? Philosophers have been thinking about radical skepticism for thousands of years, long before contemporary science developed. And crucially, I mean, radical skepticism is going to throw doubt on basically everything, or almost everything, that we believe about the external world. Now, most forms of anti-realism in philosophy of science, do not want to endorse radical skepticism. So consider, for instance, Bas van Frassen's constructive empiricism. According to constructive empiricism, science aims to give us theories that are empirically adequate, that is, true with respect to the observable phenomena. The constructive empiricist is agnostic concerning what's going on behind the observable phenomena, but they grant that, yes, of course, we get knowledge of the observable phenomena. I mean, in the context of philosophy of science, anti-realists don't tend to deny knowledge of the observable world. They don't deny everyday knowledge. They deny specifically that science gets at the truth about the unobservable, about what's going on behind the phenomena, about the fundamental nature and structure of the universe. So, anti-realists don't want to go all the way to radical skepticism. It's a more limited sort of skepticism. But according to tautological scientific realism, the only way that we can conceive of our best scientific theories turning out to be thoroughly mistaken is if a radical skeptical scenario is true. So as long as you accept common sense beliefs, as long as you accept that, you have two hands, then it's just inconceivable that the best scientific theories could be thoroughly mistaken. And since it's inconceivable, it would be irrational to believe it. So that forces you to accept realism. So basically, tautological scientific realism alleges that this sort of standard, moderate anti-realist position is just untenable. Either you go for radical skepticism and you deny knowledge across the board, or you grant that science uncovers the facts. Science uncovers the facts not just about the observable world, but about the unobservable world as well. There is no viable middle path. So that's the claim. But why is this? Well, the basic point here is going to be that the central law of contemporary science is no longer subject to genuine uncertainty. And this is because of the enormous varieties of evidence for these claims and because of the deep interconnections between different fields. So let's take a specific example. So this example comes from a paper given by Carl Hoefer. I don't really know if I'm pronouncing his name correctly. Carl Hoefer and Genevieve Marti. They give the example of viruses. So there is an enormous variety of independent evidence for viruses. They can be imaged using many different instruments and methods. They can be seen under microscopes, grown in laboratory cultures. They can be used in phage therapy. They evolve in the wild and cause various diseases. And we have all sorts of methods of intervention against viruses, like the use of vaccines. All of these things and more offer us ways to interact with and understand viruses. Moreover, there are no significant gaps in our understanding of the sort of basic facts about viruses. There are no significant anomalies in the empirical evidence concerning the basic facts about viruses, the central law about viruses. Of course, there are still plenty of things about viruses that we don't understand. We're still in the dark about the origin of viruses, for example. But the basic fact that there are viruses, right? There are infectious agents that consist of strands of DNA inside a protein coat and that hijack the machinery of living cells in order to replicate. That claim is, there's 100 reasons to postulate these things and no problems. There's no empirical anomalies whatsoever with respect to that claim. So we have like hundreds of lines of evidence, no empirical anomalies. Okay, so, I mean, in principle, like, what sort of unexpected experimental result could undermine our belief that there are viruses? Science proceeds by testing theories through observation and experiment. You have a hypothesis, you derive a prediction, you test the prediction, you make an observation. But with respect to the basic law of viruses, all of the relevant experiments have already been performed, and they all point in the direction of viruses. So there's nowhere left where we might find some anomalous result that could throw doubt onto that. You know, we can't imagine gathering new experimental data that throws doubt onto the existence of viruses because, well, as Hoefer says, the experiments have all been done already and the current theory is confirmed by them, as he says. I mean, and now, of course, there are things, like when I say we can't imagine this, yeah, there are things we can imagine, right? We can imagine God coming down and revealing that he planted the evidence of viruses to deceive us. But at that point, we're basically just imagining a radical skeptical scenario. You know, we're imagining something like Descartes' evil demon. So the question is, okay, how could this basic law be false? How could viruses fail to exist? Well, assuming that you trust your everyday observations, you can't really imagine such a scenario because, you know, we would have to suppose that all of these lines of evidence, these you know, many hundreds of lines of evidence are thoroughly misleading. Like suppose we say, for instance, that transmission electron microscopes are misleading, that the images they create do not correspond to any otherwise unobservable entities and processes. Well, okay, now there's a question, right? Why do electron microscopes appear to work so well? We don't have any other plausible explanation on the table. And why do they appear to work so well in so many other contexts? We use electron microscopes not just to image viruses, but to do all sorts of things, like build microchips for computers. So any story we tell about why electron microscopes are misleading with respect to viruses would force us to alter our understanding of a variety of other accepted claims in science. And this is because electron microscopes are applied in such a wide variety of contexts. And of course, it's not just the electron microscopes that pose a problem. Contemporary science is highly systematic. All the different parts of the law are deeply intertwined. So if our understanding of the basic law with respect to something like viruses is mistaken, then our understanding of microbiology, biochemistry, and so on must also be radically mistaken. For instance, our understanding of, you know, DNA and RNA is now open to question as well, which would then throw into doubt our understanding of how cells function, how diseases spread, and so on. Because our beliefs in all of these areas are connected to the basic law with respect to viruses. Different scientific fields are deeply interconnected, so if we're mistaken about one of them, we must be mistaken about a whole lot of other things. So if we try to deny the claim that if we try to deny this basic claim, there are viruses, then as Hoefer and Marty put it, I quote, "A chain reaction would result that winds up forcing wholesale changes across most or all of our accepted law. In effect, we would be pushed into a radical skeptical scenario of one kind or another as the only way to imagine carrying through the rejection of the initial piece of law. So rejecting the existence of viruses would force us into radical skepticism." And this wasn't always the case. Science wasn't always as systematic as it is today. That's why the replacement of, say, phlogiston chemistry with oxygen chemistry didn't really have a massive effect on other fields. So the central claims, the central law of contemporary science is very unlikely to be overthrown. The future development of science is not going to undermine our currently accepted law. Why? Well, because there's just no alternative. That's why. Assuming that we're not being massively deceived, as in a skeptical scenario. Right then, well, a quick advert. I do have a Patreon, which I upload bonus videos on that. So if you want to hear more of what I have to say about things, then sign up to that. Or you can just donate if you want to support the channel on my PayPal. I offer private tutoring in philosophy, so send an email if you're interested in that. And I have a Discord. Links to all of this will be in the description. Okay then. So, let's get back to tautological scientific realism. Here are the important points. First of all, just like anti-realists, tautological scientific realists can grant that inference to the best explanation is a poor rule of inference. Because what they would say is, look, there's no inference here from the success of our best theories to their truth. Right? We're not saying, well, these theories are true because, in virtue of the fact that they make so many successful novel predictions. Rather, the claim is that our best theories cannot coherently be conceived to be false. They cannot be conceived to be mistaken in the way that theories accepted by past scientists were radically mistaken. This is why the position is called like tautological scientific realism. We're not inferring that our best theories are true on the basis of explanatory considerations. The inference is based on the impossibility of an alternative. The second thing to note is that tautological scientific realism is not historical. Like anti-realists, tautological scientific realists can grant that there have been radical theory changes in the past, changes which have completely overturned our worldviews. So, as I mentioned earlier, this kind of, it's sometimes called the pessimistic induction. This is often presented as a challenge to realism, right? So anti-realists will sometimes say, look, many theories that were accepted in the past turned out to be mistaken, so probably many of the theories that we accept today will turn out to be mistaken. Now, in response, realists have tried to show that the situation is not as dire as the anti-realist presents it. Seemingly radical theory change was not so radical after all, because a great deal of theoretical content is preserved across theory change. So, Newtonian mechanics, phlogiston chemistry, the caloric theory of heat, these may have been wrong in the details, but, there are certain aspects of those theories, maybe the structural content of the theories, the mathematical laws described by the theories that have been retained in later theories. So we can similarly trust that the structural content of our theories will be retained in the future. That's the sort of thing that some realists might say. Again, I have other videos on that. This sort of thing raises various difficult questions, but tautological scientific realism just abandons this whole project, right? The defender of tautological scientific realism can just grant, yeah, previous theories were radically wrong. The core parts of science only became beyond a reasonable doubt in about the mid-20th century, when science became thoroughly systematic and interconnected, and the varieties of evidence for the central law ballooned. So here's what tautological scientific realism is committed to. Basically, two principles. First, if there is strong evidence for P, and there is no reasonable way to doubt that P, then you ought to believe that P. Second, if we cannot coherently conceive of how P could turn out to be false, then it is not reasonable to doubt that P. And, the claim is, well, look, these are just very basic, uncontroversial epistemic principles, and these two principles are indeed hold for the central law of science. There is, for any claim in that central law, there's strong evidence. So there's strong evidence for the existence of viruses. And we cannot coherently conceive of how it could turn out that our basic law concerning viruses is false. So it's not reasonable to doubt that basic law. So we ought to believe it. Okay, now, with all of that said, there is an important limitation of tautological scientific realism. So, Hoefer says that on this approach, realism cannot be justified for the theories in fundamental physics. We have to limit realism from fundamental physics. Why? Well, basically because fundamental physics remains highly debated. It's still sort of up in the air. First of all, we know that the central law of current physics can't be quite right. General relativity and quantum mechanics, the two central theories in fundamental physics, are incompatible. So we know they're not true because they're incompatible. So there must be some alternative out there that would account for the success of both of them, but is different from them. Moreover, there are various, if you take, for instance, quantum mechanics, well, there are various interpretations of quantum mechanics which imply radically different metaphysics. So you just take one of these theories, right, quantum mechanics, okay? We have different interpretations. There's collapse interpretations, Everett interpretations, Bohmian interpretations. These commit you to very different views about the underlying nature of reality. So different interpretations of the very same theory lead to different metaphysics. And we don't know which of those interpretations is right. Moreover, we know that the theory of which they are interpretations is not entirely adequate either. So, so there's a lot still up in the air here. Many of the people working in physics, if anything, seem to be hoping for, even expecting at some point, a paradigm shift. They're actively looking for a theory that is different, that involves a different ontology, different laws, whatever, that explains the contexts in which general relativity and current quantum theories are successful. So maybe a theory of quantum gravity or whatever would do this. Now, maybe this replacement theory will, vindicate current quantum field theories so that we'll be able to say, well, our current theories are at least approximately true with respect to the fundamental nature of the universe, right? So maybe once we have this replacement theory, we'll be able to look back and say, oh yeah, people in the early 21st century, they got it approximately right. Maybe, but maybe not. We don't yet have the replacement theory, so we can't say. We don't know how different it looks in terms of what it says about the fundamental structure and nature of the universe. So the point is, physicists are hoping for, they're expecting to find an alternative theory like this. And this situation is very different from that of, biologists studying viruses. Nobody is hoping or expecting to come up with some radically new paradigm that will just overthrow the central law of virology, by which we'll be able to say, oh yeah, there are no things that have, strands of DNA in a protein coat, right? Like that, no one's expecting that. Finally, fundamental physics is not deeply intertwined with our other sciences. Now, physics in general obviously has very deep and systematic connections to other fields. So, understanding the periodic table and the relations between the elements, that's based on physics, right? Where we appeal to the standard model of particle physics and forces between different particles and so on. Like chemical elements are atoms composed of protons, neutrons, electrons, with their interactions determined by the electrons in the atomic orbital and so on. But these sorts of claims are not dependent on whether we take the Everett interpretation or the Bohmian interpretation of quantum mechanics. Even if quantum mechanics is mistaken in its description of the fundamental nature of the universe, we still expect the periodic table will be retained. So in contexts in which physics is connected to other sciences, it doesn't really matter whether there is, for instance, genuinely a collapse of superpositions, or whether fundamental particles are are they really just excitations in quantum fields or whatever. It doesn't matter for the purposes of context like understanding the periodic table which view you take here. So, tautological scientific realism does not claim that the truths about fundamental physics will forever be beyond our grasp. It claims that at present there are large gaps in our understanding, and there are significant anomalies in our fundamental physical theories, so we can coherently imagine those theories being displaced. And that's why realism should be restricted from fundamental physics. But it doesn't claim that this is going to be the case forever, right? Maybe some paradigm shift in the future will change things so that even realism, even here, is justified. So that is tautological scientific realism. Let's turn to some objections. So we've seen that tautological scientific realism infers from the claim that the central law cannot coherently be doubted to the claim that the central law is true, putting aside radical skepticism. So, and we'll just take that for granted, obviously. Let's just take for granted that we're not radical skeptics. Okay, what is it to coherently doubt something? Here's a worry, right? You might say, well, of course I can doubt that the central law is true. Here's a couple of ways of doing it, right? Surely I can imagine circumstances in which some scientist or group of scientists build new instruments and they start to uncover surprising experimental data, and this leads to wholesale changes in our worldview. Similarly, I can imagine contacting an alien civilization whose science developed in an entirely different direction. Right, their science is just as successful as ours. They're able to, make remarkably accurate predictions, and they build technologies and so on. But the claims that their descriptions of the underlying structure and nature of the universe are just radically different. This is I can imagine this, right? These scenarios seem logically possible. There's no obvious contradiction here. So why doesn't this count as coherently imagining a scenario in which our central law turns out to be false? Well, here's what Hoefer says about this move. He says, "This is to imagine a possibility that we have no reason to think is an actual logical possibility. Without fleshing out the story in detail, i.e. without actually producing this brilliant alternative chemistry, we have no more reason to take this as a genuine possibility than we do the daydreams of a mid-20th century mathematician who imagines herself coming up with a counterexample to Fermat's last theorem." So in other words, yes, we can imagine our central law turning out to be false in the sense that we can tell a story in which this happens. We can write a fiction in which this happens, but there's no reason to suppose that it's actually logically possible. The story, as told, leaves out all of the important details, right? So just how exactly could the myriad different methods of intervention with respect to viruses turn out to be completely misleading? Just which changes are we supposing will take place to our other beliefs? We have no idea. So we have no idea whether such changes can be made while remaining logically consistent with our everyday beliefs. So there's no reason to think that the alternative theories of the new scientists or the alien civilizations are genuine logical possibilities. If you claim that they are genuine logical possibilities, the burden of proof is on you to explain exactly how that scenario is supposed to work. And obviously no anti-realist has met that burden. But I do think at this point, the anti-realist might object here. What exactly is being expected of the anti-realist? Surely the requirement can't be that in order to hold, that for all we know there might be an alternative theory, you have to put up that theory or shut up, right? That can't be the requirement. We can't expect that the anti-realist will actually produce an alternative to the central law of contemporary science that does just as good a job of that central law in terms of prediction and control. No anti-realist could ever have met that requirement, not even in the distant past. Anti-realists in the 1800s were not able to conceive of an alternative to Newtonian mechanics. It took decades of difficult conceptual work to do that. Anti-realists in the 1600s were not able to conceive an alternative to phlogiston theory of combustion. Again, it took decades of work, of just, empirical work, scientific work, conceptual work to come up with these alternatives. So if the inability of the anti-realist to present an alternative theory is what demonstrates that the falsehood of our central law is inconceivable, then it looks like scientists in the past could similarly have demonstrated that the falsehood of their central law was inconceivable. So we might say, well, look, we're not demanding that the anti-realist display an alternative theory. Maybe the demand is more limited. So we might ask the anti-realist to just give some... So when we're asking the anti-realist to give a story in which our theories turn out to be incorrect, this has to involve identifying specific problems with our current theories, or like logical contradictions or areas that are still open, where there are still like open experimental tests or empirical anomalies or whatever. We can do this with fundamental physics, right? We know in the case of fundamental physics where the new paradigm might come from. Okay, so we kind of can see like, oh yeah, the inconsistency of general relativity and quantum mechanics, that opens up space for an alternative. The anti-realist similarly needs to show that there's space for an alternative with respect to the rest of the law. But I guess, with this point in mind, we might well sort of turn the argument around here. So Hoefer alleges that it is inconceivable that our current law should turn out to be radically false. But of course, he hasn't in fact presented in detail how our current data logically entails the current law, right? So Hoefer's claim is you either accept the current law or you're committed to radical skepticism. There is no viable middle path. Now, we can grant, sure, that the anti-realist has not, actually presented an alternative theory. Indeed, the anti-realist hasn't even identified where that alternative theory might come from. The anti-realist has not shown that there is a viable middle path. But at the same time, Hoefer hasn't shown that the middle path is not viable. So again, right, we don't know what the alternative theory might look like. Perhaps we can't even see where there is room for such an alternative theory to develop, but nor can we see that this is ruled out as a matter of logical necessity. So it seems like, again, what are we demanding that the anti-realist do, right? If we're demanding that the anti-realist actually show in detail, like, how one of these alternative theories might be developed, I suppose the point would be, well, Hoefer hasn't shown, the tautological scientific realist hasn't shown that our everyday beliefs, our common sense beliefs, entail our current law, and so rule out the possibility of an alternative theory being developed. The comparison to Fermat's last theorem is perhaps telling. So today, of course, we have proof of Fermat's last theorem, and now that we have a proof of Fermat's last theorem, we can say that a counterexample to the theorem was always logically impossible, right? There was no genuine alternative scenario with respect to Fermat's last theorem. But prior to the proof of Fermat's last theorem being given, presumably, mathematicians, should have suspended judgment about it, right? If we asked them prior to the proof of Fermat's last theorem being given, if we asked them, is there a counterexample to Fermat's last theorem, then what they should have said is well, we don't know. Similarly, then, we neither have just a bit of a sneeze there. Okay. So similarly, then, we neither have an alternative science available, nor a clear way of developing such an alternative science, but nor do we have a logical proof that an alternative science is impossible. So is an alternative science possible? Well, maybe we should just suspend judgment about that. In the same way that, before we had the proof of Fermat's last theorem, if we were asked, is there a counterexample to Fermat's last theorem, we should have said, I don't know, right? Got to wait for the proof, and then we'll see. This is one concern about Hoefer's argument. Another potential objection to the argument that's worth noting is that claims about conceivability have had maybe not the best history. We might try to make a sort of pessimistic induction argument here. Consider, for instance, the development of non-Euclidean geometries. So if you take the claim that two parallel straight lines extended indefinitely will never meet, well, many philosophers have taken this as a self-evident truth of reason, not something open to doubt. It's not even conceivable that that could be false. But it turns out that actually there are non-Euclidean geometries in which that axiom doesn't hold. Not only are there non-Euclidean geometries in which that axiom doesn't hold, but in fact the very structure of our universe may be better described with such non-Euclidean geometries. So not only are there conceivable alternatives, one of those alternatives might actually be true. Or take, the law of non-contradiction. For centuries, this was treated as an indubitable law of thought, inconceivable that it could fail. But over the last few decades, the development of paraconsistent logics that tolerate contradictions, plus arguments from dialetheists like Graham Priest, has forced philosophers to take seriously the idea that, no, that law might actually be false. Maybe there really are true contradictions. Even if people like Priest are ultimately mistaken, we might argue, well, he's at least shown that dialetheism is, in some sense, conceivable. Maybe it's not conceivable, but we can't just assume that it's inconceivable. For a long time, it just seemed obvious that these things were inconceivable, but then, we turned out we were wrong. We were wrong about the limits of conceivability. And so for these sorts of reasons, we might be suspicious concerning claims about what we can and cannot conceive. Um, okay, a final point here is that there are reasons why it might be difficult for us to conceive of ways that the contemporary law could be false, even if it actually is false, right? So the anti-realist can give explanations for why we can't conceive that the contemporary law is false, and this might undermine the appeal to this sort of inconceivability in an argument for realism. Okay, so one of the features that Hoefer cites in support of tautological scientific realism is the remarkable systematicity of modern science, the interconnectedness of modern science. Rejecting any one part of the central law would force radical changes elsewhere. Our other commitments would fall like dominoes, and we would end up judging that almost all of our beliefs are mistaken. So this is one of the central claims he makes. Okay, well, yeah, grant that this is true. Why does this support realism? An anti-realist might well cite systematicity as an explanation of why we can't conceive of the falsehood of our central law, of why, indeed, why the central law will probably not be overthrown anytime soon. So we have to distinguish two questions, right? So question one is, are contemporary scientific theories approximately true? And question two is, should we expect radical changes to scientific theories in the future? You could say no to the first question. You could say that no, contemporary scientific theories are not approximately true. But you wouldn't necessarily have to say yes to the second, that, well, we should expect radical theory change in the future. An anti-realist can, perfectly consistently expect that theories are going to remain stable, that our theories are false, but they're going to remain stable. Why? Well, systematicity. Systematicity, we might argue, leads to stability. Due to the tight connections between different fields, replacing one theory requires replacing a variety of others. And, I mean, we should expect this to be the case regardless of whether the theories in question are close to the truth. It's very difficult to come up with even one theory that is empirically adequate in a given field. Consider, for instance, how Newtonian mechanics struggled to account for the stability of the solar system for so long after it was proposed. Newton recognised that gravitational perturbations among the planets would make the solar system unstable over the long run, and he had to postulate occasional acts of divine intervention from God, restoring stability. It was only with the work of Laplace and Lagrange, decades after Newton's death, that that problem was solved. Well, actually, that's a simplification. It continues to be, the stability of the solar system continues to be studied up to the present day, but they solve some aspects of it. So, we had a pretty, major, that was an empirical anomaly. It was a pretty major empirical anomaly with the theory, which took decades to resolve that empirical anomaly. So the point is, in order to get just one empirically adequate theory for just one domain, you need a great deal of expertise. Now, due to the systematicity of modern science, any alternative theory in one domain would necessitate alternatives in a host of other domains as well. But then that's obviously going to be a much harder task. However hard it is to come up with, an adequate theory for one domain, it's going to be much harder to come up with, if in order to have an adequate theory in domain A, you also have to come up with other alternative adequate theories for domains B, C, D, etc., you're obviously going to have a much harder task. On top of all of this, modern science has become increasingly specialized. Nobody has the expertise to assess a wide variety of different fields. So we have this situation where there's tighter links between different fields, while each scientist is getting a narrower and narrower and narrower focus, right? So no scientist is able to gain expertise in all of these fields and take the sort of big picture view. So given these two factors, we should expect that viable alternative theories will become increasingly difficult to conceive, even if our current theories are false. One way to think of this is in terms of peaks in an adaptive landscape, to take a metaphor from evolutionary theory. So, we're constantly searching for theories that allow us to do things, theories that allow us to make predictions, solve puzzles, provide good explanations, support the development of technologies and so on. Over time, the scientific method tends to modify theories so that they get better and better and better at these tasks. You sort of, it pushes theories up the adaptive landscape, right? They get better, they go up. But there are, we can imagine a sort of landscape of all possible theories. Maybe there are local peaks, right? A theory that's, and we know that there are local peaks because this has happened historically, right? There have been theories that were very powerful for their time, but they had limits and eventually ran into empirical anomalies, and a radical change was required. We had to jump to a completely different part of the conceptual landscape. Okay, so we had something like phlogiston chemistry. Okay, that was pretty damn good as far as theories of the world go, but it ended up there were a lot of anomalies that built up, and then we had to jump to a very different sort of framework, a very different part of the conceptual landscape, oxygen chemistry. And oxygen chemistry has driven us way higher. Similarly, the jump from Newtonian mechanics to general relativity drove us way higher. Now, here's the point. You might find yourself on a very, very high peak on the adaptive landscape, but maybe this is only a local peak. Maybe in the total space of all theories, there's some theory that would perform better or equally well, but because you've just sort of driven this theory so far, because we've now reached a peak that's so high, and maybe the alternative is so different, it's just, this alternative is now closed off to us. Partly, look, it's just very, very difficult for us to sample the landscape of different theories. Again, think about how long it took, how much effort was required to come up with to solve the problems facing Newtonian mechanics, right? Coming up with even one theory is very tough. So this is, again, just a metaphor, but it hopefully sort of illustrates the point, right? Like the idea is there are certain features of contemporary science that maybe will kind of lock us into a particular part of the conceptual landscape, but maybe we are not at a global peak. Maybe it's only local. Right, well, anyway, that was tautological scientific realism. Hope you found that interesting, and that is all I have to say for this video. Thank you for watching. Goodbye.